I'm going to be posting some chapter 2 homework, hopefully by the end of the day, so you can start chipping away at the very first ones that have to do with the infinite square well. I think there's just some problems on that, and I'm hoping if things go well, we'll sort of finish our infinite square well discussion. You know, again, all of you are familiar with that solution, but the details of how to think about it and construct other things about it are where we're really concentrating here. And so we're really, when I look through the notes, it's kind of a deep dive in certain respects that you didn't really think about probably in modern at all. Anybody have any concerns or questions before we get started? Yes, Riley. Uh-huh. Let me see. Yeah, so what is the form of your integral that you're looking at? No, the one that you're worried about doing. Yeah, just read it out to me. Excuse me. X minus x0 squared, okay.
Over 4a squared.
Uh-huh. And you just want to integrate that from minus infinity to infinity?
Well, we took the probability, so it ends up being over 2a. Like in the denominator, it's 2a squared or 4a squared.
2a squared, okay. Oh, I see. After you've taken the magnitude squared of it, you just double the exponent when you take the magnitude squared of it. And now you want to integrate this from minus infinity to infinity to see what the total area under the curve is. You're hoping it might be 1, but if it's not 1, then we'll just change this a to something else, right? And make it. So you're trying to do essentially this integral, right? Now, I can't remember exactly what the form of the one in that integral tables was, but it was something like integral from minus infinity to infinity. One of them was x squared dx. Is that right?
Yeah, that goes from 0 to
0 to infinity, right. So the idea is this integral is, well, first let's change variables, right? Because it doesn't have an x minus x0 squared in this one. It just has an x squared there. So I'm going to do a u substitution. Let u equal x minus x0. Then du is dx because x0 is just a constant, right? So let's rewrite this integral here in terms of u. Now, the first thing to realize is when x goes to plus infinity, u goes to plus infinity. When x goes to minus infinity, u goes to minus. So the limits are still integral from minus infinity to infinity. Just to remind ourselves, we've changed it and thought about it. I'll write u, we put x equals here just to make it not look confusing. E to the minus u squared over 2a squared dx. And so then I would say my lambda that, well, so, okay. This now is, dx is du, forgot to change that. This now is a symmetric function with respect to u equals 0, right? I mean, it looks like this. And so isn't it 2 times the integral from 0 to infinity? And then 1 over 2a squared is my lambda. So that's how you make that transformation.
You don't have to worry about like how u and x are different. Like you don't have to reset back in like the x minus x naught.
No, once you've done the integral, you've got the value for the integral. So there's no, there is no x dependence in the final answer. So we're thinking of it as, this is a number. let's figure out what that number is, and we'll get the number. If we change variables for the integral, that's fine. We still got the number. We don't have to substitute anything back in. Sure. And it's the same way later on in that kind of sequence of problems. You'll be wanting to do integrals like this, or maybe even like that. But still, when you do that U substitution, it sort of throws it into the form that's there, that's in the table that I linked to. I think there's some equivalent integrals, maybe in a slightly different notation in the inside or back cover of Griffiths. I can't remember, but there are some Gaussian integrals. They look a little bit different and they just weren't quite as clear. So I thought these were better ones to link to. Okay, let's go now back and remind ourselves where we were. Let's see, we did some voting questions. Oh, maybe we'll start here. Like we were solving the infinite square well problem. And just to kind of summarize where we were, sorry, I just want to make sure. There we go. Wasn't sure I was actually sharing the screen. There we go. Current slide. So what were we doing? Well, we want to solve the time-dependent Schrodinger equation in the context of this potential. And we decided, well, we're going to separate variables. And so a sub-problem is to find all the solutions to the time-independent Schrodinger equation. Make this product solution. And then because we found an infinite number of solutions to the time-dependent Schrodinger equation, we can take an infinite linear combination of them. And the hope is that if you're given some initial conditions, we can actually figure out these CNs. We haven't done that yet, but we will do that in an example and in a worksheet today. Okay. Uh-oh, can't see because of this thing, but let's move it. Put that on the side, no. So we applied some boundary conditions, right? We said, oh, psi has got to be 0 outside of the well. Inside the well, this is the time-independent Schrodinger equation. And we said, we got all these constants E and this stuff. Let's just define a simplifying constant K that's related to E this way. We get this harmonic oscillator differential equation. And you all have probably memorized what the solutions are to that. So linear combinations of cosines and sines of Kx. And then we've got to apply boundary conditions, right? Because we had cosines and sines inside the well, 0 outside. We made a detailed argument about why psi had to be continuous, but this was one of those cases where psi prime is not required to be continuous. So we just required that psi is continuous at x equals 0 and at x equals a. The requirement that it's 0 at x equals 0 just says, oh, sorry, this should be a sine there, and this one should be a cosine to be consistent with what's down here. Pretend that's a sine, pretend that's a cosine, right? Doesn't really matter which order we write them in. We found out that the coefficient in front of the cosine has to be 0, and so then our simplified solution that makes it continuous at x equals 0 looks like this. It's either a sine kx or 0. And then we have to require that psi is continuous at x equals a. That required that this be true. A can't be 0, and therefore it must be sine ka that's 0, which says that k has to have this weird range of values. K has to be a multiple of pi over a, where the multiplier is an integer starting at 1, any positive integer. And therefore, the allowed energy values, it's easy to forget. We found some allowed K values, but K was related to energy. Up here at the top, we have the relationship between K and energy. So if we have some allowed Kns, let's retranslate that back into the allowed ENs, and that gives the formula that, so long ago in modern, you remember. the one down at the bottom, n squared pi squared h bar squared over 2ma squared. Okay. So just to summarize, boy, this is really tough in full screen mode. I think I had a better solution before. If you'll bear with me for a second. Slideshow, setup slideshow. Okay. Current slide. Hopefully that's better. Okay, and I think that where we ended was that, you know, you can normalize this. It's not my favorite integral to do. You have to integrate a sine squared of something, but you know, you do some trig identities and you're able to work that into something, an elementary integral, and you find out that a has to be √2 over a. So this is our full solution to the time independent Schrodinger equation. And then the full solution that we found to this time dependent Schrodinger equation has the product form of the psi n that's above times the corresponding e to the minus en t over h bar, where en is given by this. So this whole thing in the box there is our infinite number of separable solutions, or we could also call them stationary states or energy eigenstates for the infinite square well potential. And of course, as you know from modern, we usually call the lowest allowed energy eigenstate or separable solution the ground state, and all higher ones are excited state. So above that would be the first excited state, then the second excited state. And the energies, the allowed energies, are proportional to n squared, and that means the separation between energies keeps getting bigger and bigger as the energies go up, right? The energy spacing just gets larger and larger. That's not always true. We could also say, in terms of the notation we've been developing, the Hamiltonian has a discrete spectrum for this potential. It's purely discrete. There's no continuous part. That means the allowed energies have gaps between them, and they're all that way. There's no places where there's a continuum of allowed E's. Okay, let me just make sure I'm not forgetting anything here. Good, let's, well, given this formula for the allowed energies, I think there's a voting question here. If you've got your voting cards with you, that's something you should always bring, but if you don't, just hold up fingers. Here we got 1, 2, or 3, just because it's hard to remember this when it's been a while since you've been in modern. Here's the allowed energies down here. How does the energy for the n equals 3 state, we might call that the second excited state because n equals 1 is the ground, at least in this way of numbering, of an infinite square well of width A, compared with the energy of the n equals 3 state of a well that has a larger width. So here, just in this cartoon, here's the width of the well we're talking about. We're going to make that well larger. How does the energy of the second excited state, n equals 3, compared to it in the more narrow well? Lower, higher, or the same energy? I got to decide on my. Yeah, it looks like everybody's agreeing A, that it's lower energy, and I agree. Notice that what's important here is that A is the well width. As A gets bigger, each En gets smaller for each corresponding N. Right? Okay, let's look at that applet that I showed you before. Let's hope this works here. All right, and I'm supposed to, let's see. I've got some notes on what I want to do with this. So let's go back here. Narrow the well width a little bit. Let's remove so many of the things that are on here. Let's clear this for a second. Okay, so the allowed energies, I'm not sure what this value is down at the bottom, but here, let me narrow it even more so that we can see those energies. The allowed energies are shown in gray. So that one that's highlighted in yellow now is the ground state energy, and the ground state wave function is shown down at the bottom. It's 0 until you get inside the well, and then it's got a single hump that's shaped like a sine function, right? If the left edge is at 0. There's the first excited state, there's the second excited state. They're all sine kind of functions that go to 0 and they match up exactly. So where the sine function is 0, it exactly continues on at 0 once you go outside the well. And each time you go up in energy, you get one more bump, right? So here we're in the third allowed state. There are 3 bumps, an upper bump in the middle and 2 lower bumps there for those solutions. If I click on this state, well, let's click on the ground state, for example. This particular app shows me the probability density. So this is just the magnitude squared of that function. And that's showing me that the probability of finding it outside the well, of course, is 0. The color is supposed to be showing me what the phase of the wave function is as a function of time. That means it's multiplied by e to the minus I E1 t over h bar, which is basically moving it around in the complex plane as time goes on. And so those colors just showing you that the wave function is changing phase as time goes on. Okay. Now, these solutions are not the only solutions, but they're very special solutions. Here's a question on here, I hope, about other solutions. So all separable solutions have the form psi, so they're separable. That means they're a product of a spatial part and a time part. Omega here is just E over h bar. So I stole this slide from somebody else and they just used that omega notation instead of the E notation. So let's consider the sum of 2. So all of these, what we said is so impressive about these solutions that we've proved is that the probability density as a function of x is independent of time. In fact, we claimed it's true as a function of any variable, but we don't know how to produce those other probability densities yet. What if we take a sum of the ground state, that's n equals 1, and the first excited state, n equals 2, and we add them together? So we say my particle is not in the ground state, it's not in the first excited state, but it's in a sum of those 2 states. I'd have to normalize it, of course. If I do that, is the corresponding wave function stationary? Which is to say, stationary means the probability density, which could be a function of time, is actually time dependent. Is that true? Yes, period, no, period, or it depends. We're talking about the probability density associated with this wave function right here. Sum of 2 stationary states. Think about it for a second. Okay, let's see a vote on it. I don't know, maybe there's confusion. It doesn't look like all of you are ready to vote, but. Okay, show it so I can see it. You know, there are votes for everything and no clear winner. There might be one more A than everything else. Anybody want to argue one way or the other who feels very strongly about their answer? Yeah, I mean, we can sort of think from the point of view. Let me just unshare the screen here. Ooh, wow, that's really out of focus. Let's see if I can get it to focus here. There we go. Why does the time dependence, you know, if I take the ground state energy wave function, energy eigenfunction, so it looks like this. Psi 1 of x, we won't worry about the form of that. times e to the minus I e1t over h bar. Why is it a stationary state? Well, so that's our capital psi1 of x and t. Why do we call it a stationary state? Because when we take the magnitude squared of it, there's no time dependence. The magnitude squared is the probability density, and the time dependence goes away. Because when I do psi star psi, I get an e to the minus I junk times e to the plus I junk, and they cancel out. So what happens in this case where we, instead of this, I have this plus psi2 of x e to the minus I e2t over h bar. Is the time dependence going to cancel out when I take the magnitude squared of it? I mean, sort of a pain to write, but let's say I want to calculate rho of x and t, right? What I would do is just take the magnitude squared of this. Let's see. Psi1 e to the minus I e1t over h bar. I'm going to leave all the time stuff in because we need it. Plus psi2 e to the minus I e2t over h bar. That's my psi. Now let's multiply by psi star. Psi1 and psi2 are real. So I don't need to really star them, right? Their complex conjugate is the same thing back. So I'm going to get a psi1 times e to the I et over h bar plus psi2 e to the plus I e, this should be an e1 e2 t over h bar. When I FOIL that out, if you like, is it going to be, is all the time dependence going to cancel out? Some of you are shaking yes and some no. Anybody want to make an argument one way or the other? It certainly is true. This is supposed to be a 1 right there. In the first term, when I multiply first times first, the time dependence cancels out, right? Because I get a e to the minus I e1 stuff, e to the plus I e1 stuff. Same thing for last. But outer and inner don't cancel out. Outer and inner actually don't cancel out. And so it isn't time dependent, which, when we find the energy eigenstates, we usually say those are the stationary states. It's not surprising that a linear combination of stationary states is not a stationary state. Otherwise, it would have been in the list. So linear combinations and, a sum of two things is a kind of linear combination. A simple one is, you can work that out and simplify the function, but there is a time dependence to it in the outer and inner terms. Okay. What's next after that? Sum of two solutions. Okay. Griffiths lists some properties of these time independent. So we're not talking about the full separable solution, but rather just the time independent Schrodinger equation solutions, right? That look like this. We haven't put in the time part. So what are the properties of the lowercase psi n's? They're either even or odd with respect to the center of the well in this case, right? Because we have ones that have just a single hump, that's even, and then the double hump one, that's odd, and then even, and then odd, and so on. Each higher n value has one additional bump in it, right? It either goes up one more time or down one more time, one or the other. The collections of them are what we will call orthogonal. Remember before I was sort of speaking as if these functions, just like x hat, y hat, and z hat, form a basis for the three-dimensional vector space that we're used to from introductory physics. These functions, or equivalently, the function of this times the function of t, but even these functions form a basis for a collection of all functions as a function of real variables. But there's an infinite collection of these, so I'm going to think of them as basis functions. And just like the x hat, y hat, and z hat basis vectors are mutually orthogonal, right? That means if I take x hat and dot it into I hat, x hat and dot it into y hat, or z hat, I get 0, right? If I take x hat and dot it into x hat, I get 1. That means it's normalized. So one expression of that, and the way we're going to generalize the notion of a dot product, is something called an inner product between two functions here. So this is like the inner product between these two functions when we think of those functions as vectors. And maybe I won't say too much more about this right now, but I'll talk about it in more detail later. So think of this integral is how you take the inner product between two functions. So here I've got the mth one with the star on it and the nth one without the star on it. We can think of that as the inner product between psi m and psi n as vectors. They're kind of basis vectors, just like x hat and y hat would be. And the claim is, just like basis vectors, their inner products are either 0 if you're talking about different basis vectors, that's if m is not equal to n, and they're 1, the inner product is 1 if it's the same basis vector. That's like x hat dot x hat. I don't know if you guys have encountered, at least if you haven't taken 350 before, the Kronecker delta function. Do you talk about that in modern physics? Does Harris have that in the book? Kronecker delta function is just a very compact symbol for this. So delta mn means something that is 0 if these two indices are, we sort of think of it as a matrix or an array, right? And as a function of m and n, if m is not equal to n, it's 0. And if m is equal to n, it's equal to 1. So it's really the same as this multi-part function that I've got up there. Oops. Okay, so if we think of them as being vectors, they're like a set of basis vectors that are mutually orthogonal. And if we've bothered to normalize them, and we usually have, they're a set of orthonormal vectors, just like x hat, y hat, and z hat are. Yeah?
So in that first term, psi m, did you say that the star is just it's different from psi n, or something?
It's the complex conjugate. And in this case, normally we don't think there's any difference between x hat dot y hat and y hat dot x hat. But in more general cases, it makes a difference which one comes first. And that's because we're talking about complex valued functions here. If if we were talking about a vector space that could have complex values, we would probably make a distinction there between which one comes first and which one doesn't. So here, when you take the inner product between psi m and psi n, or the dot product, usually people in this context call it an inner product, but it means the same thing. It matters, whichever one goes first gets the star, whichever one goes second doesn't get the star. And when you switch it, you get the complex conjugate of the inner product. So it's not a whole lot different. It's just that one way you get the complex conjugate of putting them the other way. This collection, again, just arguing an analogy with what you know about x hat, y hat, and z hat, we say in our three-dimensional vector space that we're used to thinking about in introductory physics, x hat, y hat, and z hat are a complete collection for a basis. Usually when we talk about a basis, we mean it's complete, which is when you say it's complete, if I took just x hat and y hat, and we're talking about a three-dimensional vector space, you can't build all vectors out of just 2 of those basis vectors, right? So the collection x hat plus y hat wouldn't be a complete collection of orthonormal vectors, because I can't write an arbitrary vector in terms of just 2 if we're talking about an arbitrary vector in three-dimensional space. It's the same way here. So the collection x hat, y hat, and z hat is complete, and that means that any vector can be in three-dimensional vector space, can be written in terms of those. These functions are complete in the sense that if we have any function that is, it's got to be 0 in the regions where v is equal to infinity, but it can really have any shape that we want in the middle of the well. We should be able to write that function as a linear combination of these psi n's. Okay, so you give me an f of x, it's got to be 0 outside the well. But inside the well, f of x can have any shape you want. Now, there are some restrictions. It can't be infinitely discontinuous at every point, or all those pathological functions that mathematicians like to think about. Certainly, any continuous function this is good, but even lots of discontinuous functions can be written this way too. Can be written as an infinite linear combination of the psi-n's. So the psi-n's are like a basis, and we can form an arbitrary function out of these very special functions. Okay. I feel like there's one more thing I wanted to talk about here. Yes, well, I guess what's not in the slides there, so let me unshare this, is how to find the CNs. That's important. I'm assuming Griffiths talks about that here. So let's suppose, let me start with where I ended on that slide. I've got a function that's 0 outside of the well, but it's got some crazy shape inside the well, nothing special about it. And the claim is, if this collection of psi-n's is complete, it's like a basis. We call it an orthonormal basis. There's some complications for why people don't call it just a plain old basis. We should be able to write an arbitrary function with any shape we want inside the well as a linear combination of the psi-n's. This is like my x hat. I'm putting numbers in front of it, and so just the same way you would say, oh, if I call my basis En hat, where n equals 1 to 3. E1 is supposed to be like my x hat, E2 is my y hat, and E3 hat is supposed to be like my z hat. Couldn't I write any vector I want, in this form? We don't usually write it this obscurely, but the sum from 1 to 3 of Cn times En hat. Right, the En hats are nothing but the x hat, y hats, and z hats. We're doing the same thing here, except we need an infinite number of basis vectors here. The question is now, if I want to do that, how do I find the CNs? And there's a trick to finding the CNs. And that is using the orthogonality of the psi-n's and the psi-m's. So what we're going to do is, we're going to start with this equation and do something to both sides. And the first thing I'm going to do on both sides is multiply. So let me rewrite this down here. The first thing I'm going to do on both sides is multiply by psi m star, which is a function of x. Let me do that over here. F of x psi m star of x. And then I'm going to integrate both sides from minus infinity to infinity with respect to x. As long as I'm doing the same thing to both sides, that should be fine, right? Two things are equal. You can do anything you want to both sides. They should still be equal. Now, the claim is here, you can interchange a sum and an integral here, right? The sum doesn't have anything to do with x, and the integral doesn't have anything to do with n. So, just like when you interchange an integral with a sum over 3 values, the claim is here you can interchange it over, I can put the integral inside the sum and just let it act on the things that are functions of x. This is not a function of x, so I can actually take this integral. I'm not going to rewrite this one step, sorry, but I'm just going to rewrite my integral, move it through the sum and move it through the Cn, because Cn is a constant, it doesn't depend on x. It just goes outside the integral. Now, what did we say about this integral with respect to orthogonality of the basis functions? Yeah, it's that Kronecker delta function. It's either 0 if m is not equal to n, and it's 1 if m is equal to n. And we just abbreviate that by the Kronecker delta function. Kronecker. It's sort of analogous to the Dirac delta function, but for discrete cases rather than a continuous integral, it works the same way for discrete sums. You can think about why that is. Okay, so let's think about this sum. We've got an infinite number of terms in the sum, right? 1 for n equals 1, 1 for n equals 2, okay? And there's a term here that's only non-zero for one of those n values. It's only when n equals m, right? So I might think I'm summing over things here, right? I've got the n equals 1 term, I've got the n equals 2 term, And then somewhere way out in the series, I've got the n equals m term, and it keeps going on. This thing is only non-zero when n equals m. That's the whole point of a Kronecker-Navier function, right? So that's saying, yeah, I thought I was summing an infinite number of things up here, but I'm actually only summing up one thing because the rest of them are zeros. It's only when n equals m, I'm summing over all n's, but only one of them is going to equal m. And so I can replace the right-hand side with, get rid of the sum, because there's no infinite sum, there's only one term. And the only term that is non-zero is where n equals m. So I'd replace all the n's with m's. Sorry, I forgot to do it there. This was delta mn and delta m, and if n is equal to m, this is equal to 1. Okay. So what that tells me is that Cm is equal to this. And if I've got a formula for Cm, I also have a formula for Cn, right? As that's just, m is just an index. I could call it m or n as much as I want. So now that I've got a formula for Cm, I wanted a formula for Cn, but it's really the same thing. We found out that Cn is the integral from minus infinity to infinity of our function integrated against psi n star of x with respect to x. Okay, so we used the orthogonality of this set of functions to be able to get a formula for the Cn. That's pretty easy. Now I do have to do an infinite number of integrals, right? If I want to get C1, I have to integrate, maybe my function is like a parabolic function, which then goes to 0. Okay, I have to integrate it against psi1. That will give me C1. I have to integrate it against psi2. That would give me C2, and so on. I have to keep doing it, but I could do it each, one by one for each of these. They're not necessarily all easy integrals to do, but if nothing else, you could do this integral numerically and get a very good decimal approximation for this Cn. So I can always, maybe I only need the first 6 terms to get a very good approximation. Usually those Cn's will, like in any series, in order to be convergent, you better hope that these terms get smaller and smaller and smaller. The way they get smaller is the Cn's get smaller. These functions aren't necessarily getting any smaller. They're wiggling more wildly and wildly. But the Cn should get smaller and smaller and smaller. Maybe you only keep the first 5 terms, and that's a good enough approximation to the real way of writing that function. Okay. So these properties, let me go back to sharing the screen now. The properties are quite general. And all of them except one are true for an arbitrary shape potential. In order for one to be true, for them to be alternately even or odd with respect to the center of the well, you've got to have a symmetric potential. Okay, so one is only true for a left-right symmetric potential, like the one we're considering here, but all the other properties are true for any potential. Okay. We're supposed to do, well, let's do 2 quick voting questions, then we'll spend the rest of the time on a worksheet. At t equals 0, could the wave function for an electron in an infinite square well of width a be this function? It's got a sine squared in there. It's not like our sine function that we were used to, right? It's got a sine squared in there. Could this be the wave function that solves the time-dependent Schrodinger equation at time t equals 0? And I see I've clicked ahead too far, and I've indicated that my clicker is not so great. It goes ahead. Maybe you didn't notice it, but it actually showed the answer there. The answer is yes. A lot of people say no, because they think, well, it's not one of the psi n's. This isn't any of the psi n's. The psi n's have a sign here, right? It would be a sine of n pi x over a. This is none of those. But the point is, it doesn't have to be. It's some random function, and I can always write it as a linear combination of those at time t equals 0. So what we're saying is, At time t equals 0, it's not in the n equals 1 state. It's not in the n equals 2 state. It's in an infinite linear combination of all the psi n's. And that's fine. Your initial condition doesn't have to be in an energy eigenstate. It can be in some linear combination of them. And in general, this is going to require an infinite number of those psi n's. So you're going to have to take an infinite linear combination. So the answer is yes, it can be. Okay, any questions on that before we do a follow-on question? Okay, this is related. Okay, if you believe that at time t equals 0, the wave function is in this state in between 0 and a and is 0 everywhere else, right? Which of the following is true about the wave function psi? Okay, so this is what it looks like at time t equals 0. Now we want to put in the time dependence so that we get psi as a function of x and t. Which one of these or none of these is the correct way to put in the time dependence and turn that initial condition, this is what the shape looks like at time t equals 0, into a full-fledged function of time that's valid at later times? All right, let's just see a quick vote. Maybe you guys, maybe there's no consensus on this, but we can discuss it if not. So hold up a random number if you have no idea. Let's see. I see 1D. The correct answer is actually D here. I know, always disappointing when it's none of the above. Sort of, I count that as half of a trick question, right? When it's none of the above. The idea is well, so let me ask this in smaller parts. And let me unshare the screen so Alvis can see easily. Suppose it were in the ground state at time t equals 0. So suppose I said psi of x at time t equals 0 happens to be exactly the ground state. It has the shape of that ground state thing, right? So that's what it, so this is a function of x, right? It looks like that sine with one hump and then it goes to 0, right? That's a perfectly legitimate function of x. If that were true, how would I put the time dependence in there? What would I do to the right-hand side? The corresponding e thing, right? Which, you know, you got to say it enough times that you remember it. E to the minus I E1 t over h bar. Okay, let's do another example. Suppose at time t equals 0, it were, you know, we're in a linear combination. I know this won't be normalized, but let's not worry about the fact that it's not normalized. Here it's in a linear combination of 2 stationary states. So it's not a stationary state, as we said before. It's in a linear combination of 2 stationary states. How do I now turn this into a formula for time dependence? Yeah, I do it. Yeah, I have to put in the corresponding fact. You know, I take each one of these time-independent Schrodinger equations and turn it into its time-dependent version. So I multiply by e to the minus I E1 t over h bar. If I were smart, I would have left myself more space there. And this one gets a factor of e to the minus I E2 t over h bar. It's wiggling faster because E2 is bigger than E1, and that determines how fast it's wiggling around with respect to time. Now, in this voting question, we said at time t equals 0, it was, you know, something that's not this. It's not just a sum of 2 of them, but it involved a sine squared function, but we found out that that can be written as a infinite linear combination, Cn, of the psi n's. That was that completeness statement. And we just found out how to find the Cn's if we really want to go to the trouble. But the claim is at time t equals 0, I could write it the way it was given, but I could also express it this way. Now, if I want to put in the time dependence, it's actually easy. For each psi n, I change just that time-independent Schrodinger equation to make it a full solution to the time-dependent Schrodinger equation, e to the minus I en t over h bar. So I've got a different one of these for each term in that infinite sum. And that's how we make it time-dependent. Okay, what works for the one solution works for all the solutions. Good. Any questions on that before let me pass out a worksheet and I'll ask questions while we're passing it out. We're gonna do problem 1, keep the worksheet. I'm sure we won't get to problem 2 today, given the time. Just because I like to keep beating things over the head, the first thing you have to do is normalize this wave function. Again, I gave you an easy function here that makes your integrals simple. It's a multi-part wave function that's either, it's a constant value or 0 inside the well, but it's not constant all the way across the well. And first you're going to normalize it. So this is the one I posted on the website, Alvis.
Let's see.
It should have been posted on Friday, and it says worksheet to be used in Monday's class. And we're doing just problem 1. I don't think we'll get to problem 2 today.
Oh, here we go. Let's see.
And I suppose, since you may not have it in front of you, it's in your notes, but what was the formula for doing part B for Cn? Here's what it was. The end point was this. Notice that for us, the psi-n's are all real, so that star doesn't really come to anything here. But in more general contexts, we might need that star. Our psi-n's are all sines or zeros, so they don't have any complex numbers in them. Just for checking purposes, in A, I get that the normalization constant is √2/a. That has nothing to do with the √2/a that you've probably memorized for the other ones. This would have been different if it were non-zero from 0 to a/4. It just happens to be √2/a in the way I gave it. So that's what you should be getting. If you're not getting that, ask me to come over and see what you're doing. I try to keep forcing you to do the same things over and over again so that it just becomes rote after a while. So our function f of x in B is the psi of x0. We want to be able to write psi of x0 is an infinite linear combination of the psi n's and find the coefficients, and there's a formula for it. Well, the only thing we know how to do is this, find, right? And, well, it's kind of a mess, so I'll probably go through this with you. I was sort of waiting to make sure everyone got through B, just because of the time. We'll go through that in a second. It looks like many of you have at least gotten substantially into B, and I think we'll go through it together and discuss it, because it's hard to know exactly where to stop with the formula in order to make sense of it. But what I'm doing is this. If we know psi, capital Psi at time t equals 0, and we want to write it as an infinite linear combination of the lowercase psi n's with the motivation, then that makes it easy to put in the time dependence later on, right? That's why we're doing this. The claim is that we just proved a little bit earlier, this is the formula for the CNs. Right, so I've got to do this integral. Let's do that together, and I'm going to just, for the sake of time, root 2 over a. Okay, here we go. So I'm calculating this integral. I've got them in a different order here. Oops, lost touch with the screen. So I've got them in a different order here, but my psi at time t equals 0, I'm sorry, my psi at time t equals 0 is a, which is root 2 over a, only between 0 and a over 2. So normally when I calculate the CNs, I have to integrate from minus infinity to infinity. But my psi at time t equals 0 is only non-zero between 0 and a over 2. So I can reduce the integration range to the range where it's non-zero. In that range, the value of the function you found is √2/a, that's this right here. And then the formula for psi n star, well, it's real, so it's the same as the formula for psi n. That's the one you remember from modern physics, right? √2/a times sine n pi x/a. And those integrals, I can do all of them just as a function of n because it's just integrating a sign, right? The other constants go out in front, so that √2/a times √2/a gives me a 2/a. And when I anti-differentiate this sign, it turns into a minus cosine, and I get a chain rule factor, you know, in the way you anti-differentiate. Or you could just say let u equals n pi x/a and do it that way, right? Change variables with a u substitution if you really wanted to do it that way. Most people remember how to just do it without doing a u substitution, right? This turns into a minus cosine with this factor that comes out in front from the chain rule. And then I have to evaluate that antiderivative between 0 and a/2. And when I do, I get this formula over there. So in one sense, I could say, I'm done. Look, I wanted Cn over here, and I've got an explicit formula as a function of n. There's an n inside the cosine, and there's an n in the denominator there. But at another level, you might say, I have almost no intuition about that formula. Maybe I should figure out some specific number so I can see what the trend is, okay? It's looking good because the n, you know, at least they're getting smaller as time goes on. I've got an n in the denominator, so the Cn's are going to keep getting smaller. That seems somewhat important. So let's just look at the cosine of n pi/2, right? N is starting at 1. Cosine of pi/2, what's that value? 0. Cosine 2 pi/2, that's the cosine of pi. That's -1, right? So that's what I'm showing down here. This is just expanding out the cosine of n pi/2, and it keeps repeating those 4 values over and over again as I go around the circle by 90 degrees every time, right? Then when I subtract 1 from that, I get -1, -2, -1, 0, -1, -2, -1, 0. It keeps repeating over and over again. But nonetheless, the coefficients are getting smaller because I'm dividing by n there. And so if you put all the things together, you get some numbers that sort of slowly get smaller and smaller and bounce around in all sorts of crazy ways. I don't know a whole lot to say about it other than that, but at least we got something more explicit than the formula that I halfway stopped with there. Any questions about those? Sometimes we'll be able to simplify the formula a little bit. In this case, not so much. The third part I know none of you really got to, but we're supposed to find the expectation value of energy. And this is kind of a mess, but it motivates something that I'm going to mention probably right at the end of class today. Here's the definition, right? We said for any operator Q, you sandwich it between psi star and psi and integrate. That's by definition gives us the, or not by definition, that's what we, you know, we figured that out in chapter 1. Our psi at time t equals 0 is kind of messy. It's an infinite sum, right? We figured out a formula for these Cn's and it's an infinite sum, but I'm just gonna not worry about it too much. I'll just put that big mess in there. Here's my psi star. The Cm's might be complex, but the psi m's are definitely not complex. I can take away the star there if I like. Okay, let's start hammering away at this. The first thing to realize is that when this h, which is acting to the right, it has a, you know, h doesn't care about sums. So this is a linear operator. It will distribute over a sum, and it passes right through a constant too. Remember, your h really has derivative, second derivative with respect to x. So it's only going to act on the psi n. And that psi n was chosen because it's a solution to the time-independent Schrodinger equation. H acting on psi n is En times psi n back again, right? So that's what I'm replacing here in the next line down here. And then what I'm going to do is push this integral over x through the sums. So I've got a double sum there, but I can really think of it as one big sum. And I can integrate term by term or push the integral through the sum. Here's what that looks like. Let's push the integral through until we hit a function of x. This psi m star only depends on m and x. It doesn't depend on n. So I'm free to push a function of m through the n sum and just pull the sums out in front here. So I'm making sure to keep things in an order that if anything depends on the index of the sum, I keep it in front of the sum. And if anything depends on the integration variable, that's x, I keep it inside the integral. That's interchanging integrals and sums there. And now I see something that looks promising. Hey, this showed up before. What's this integral here? It's a Kronecker delta function. When I substitute in that Kronecker delta function, that means I've got a sum over n's here and something that is only non-zero in one of those terms when n equals m. So when you do that, what happens here? The first sum, the second sum, the n sum, goes away and we just keep what comes in front of it and change all the n's into m's. So what comes in front of it is cm star, cm, em, and there's a typo in my notes there. I had an n, or at least that's how it looked when I looked at it. That should be an m right there. And the second sum, the outermost sum, doesn't go away. The delta function, Kronecker delta, killed off this first sum, but the second sum is still there. Okay, now cm star, oh, I see it's 1241. So let's just stop here. Cm star times cm is the magnitude of cm squared. And so we've written the expectation value of energy in terms of these CNs, which we've managed to calculate. It wasn't a very nice formula. And we've written it in terms of them and the allowed energies there. And I'm going to start on Wednesday talking about a claim that Griffiths makes at this point in the book about the relationship between, oops, I'm not sure what happens there, the relationship between the magnitude of Cn squared and the probability of an energy measurement yielding the nth energy level. Something we can't prove now, but we'll actually postulate it in chapter 3. We're just not there yet. Griffiths makes a statement like it's obvious. It's not obvious here. We need to postulate it in chapter 3, but he's sort of thinking ahead and mentions it casually on the side. Okay. I think before Wednesday, I haven't updated the website yet, but I'm going to put chapter 2 homework on. You're also going to read section 2.3 in the book, which is on the harmonic oscillator, your old good friend, right? Do you do that in modern physics or no? I can't remember. Yeah. So we'll go much deeper than you did in modern physics, just like we are here, try to understand it. But it's good to really feel like you understand all the ins and outs of the infinite square well, because it's sort of the easiest, most beautiful set of solutions. They only get kind of more ugly from here, or at least less familiar. All right, and Tanner and Jake, if you got your homework, just make sure you get that to me so I can get it graded.